I read one science fiction story where the bad guy gets thrown into a black hole and he screams. In fact, he screams forever. I'm Dr. Michio Kaku, professor of theoretical physics and best-selling author of The God Equation. And I'm here today to answer your questions on Twitter. This is Physics Support. Cal is not a cow. Ask, y'all, why do atoms want to bond so much? Why don't they just stay single? You aren't missing anything. Atoms want to bond together. That's why we have molecules. That's why we have people, DNA. Our universe is based on atoms which like to bond with each other. The electron vibrates back and forth, binding them together. And that's why we have molecules. That's why we have you. You are a consequence of the fact that electrons are shared between different atoms using the laws of the quantum theory. Deborah Morozak asked the question, what's your favorite law of physics? Mine is momentum conservation. Well, my favorite law of physics is the equivalence of matter and energy. Einstein's equation, E equals mc squared. This is why the sun shines. It's why the stars twinkle. It's what lights up the universe. We like to think that matter and energy are totally different things. How can a rock turn into energy? However, if that rock is uranium and that energy is the fireball of a nuclear bomb, you realize that matter and energy are two sides of the same coin. Matter energy is one unit, and they can flip into each other under certain circumstances, like in the heart of a star. Sean Harris at InfoSec Hotspot asked, does anyone know of people like Michio Kaku that can explain string theory like he does for people like me, and I'm not a genius? Well, I am Michio Kaku, and I'd be glad to answer that question. First of all, most textbooks say that an electron is a dot. Particles that we see in our atom smashers are dots. But if I had a super microscope, I could see that that dot is actually a rubber band. From a distance, this rubber band looks like a dot. Close up, you see that it's a vibrating string. Now, this rubber band can vibrate in many different modes. Each mode can be called a particle. So, for example, this might be an electron. But if you twirl it in a different way, it becomes a quark. And if you twirl it this way, you have to give it a different name. We call it a neutrino. Now, how many ways can one string vibrate? The answer is obvious. An infinite number of vibrations on the same string. And so we think that all the subatomic particles of the universe, the quarks, the neutrinos, the mesons, the protons, the neutrons, there's a galaxy of these particles. They're nothing but musical notes on a tiny rubber band. A rubber band so small that it looks like a dot. So what is physics that we had to struggle with in high school? Physics is the harmonies of vibrating strings. Physics tells us how these vibrations move. What is chemistry? Chemistry is when these strings bump into each other and form molecules. Alex at Kiranskong asked, what is a quark? What is OMG?
Yeah, it's a, oh my God.
Oh. We think that inside the proton, there are three quarks, subatomic particles that make up the protons and neutrons, which in turn make up our universe. Here's a question from Rick at Sojourner99. We live in 4 dimensions, but can see 3. How many dimensions are there? Einstein says we live in a 4-dimensional world. We can go forward, backward, left, right, up, down, and the 4th dimension is time. But now we're beyond Einstein, and we have to go beyond 4 dimensions to perhaps, let's say, 10, 11 dimensions. But where are these other dimensions? We think they have curled up. They're so small that you cannot enter them, but perhaps we can feel their effects. And where is this other dimension? It is off the plane of your universe. Perhaps a parallel universe hovering right above your universe in another dimension that we cannot see or touch, but perhaps there's a gateway connecting them. That gateway is the wormhole. It was Einstein himself in 1935 who introduced the concept of a wormhole, a gateway between higher dimensional universes. Well, the next question comes from Jay Mozak, who asks, the quantum universe. Was Einstein wrong about his theory of relativity? Yes and no. There's a famous quote where Einstein said, the more successful the quantum theory gets, the sillier it looks. He thought that atomic physics, that is, quantum mechanics, was incomplete. When the Nobel Prize was given to people like Heisenberg, he said, yes, give them the Nobel Prize. They're onto something. And so Einstein had reservations about the quantum theory as the final theory. He thought there had to be a higher theory, a theory even beyond the quantum theory. So Einstein was not totally incorrect. UCHENNA LAING asked, what is the God equation? Well, Einstein spent the last 30 years of his life chasing after the God equation, an equation perhaps no more than 1 inch long that would allow us to, quote, read the mind of God. A theory that would unite the two branches of physics. On one hand, we have the theory of the big, general relativity, black holes, big bangs, and the theory of the small, quantum theory, atomic physics. How can you unite these two into one theory? At the present time, these two theories hate each other. They're based on different mathematics, different principles, different concepts, and yet we believe in our heart of hearts there has to be a master theory out there, the holy grail of physics. And that, we think, is the God equation. The leading and only candidate for that is string theory. And by the way, if you ever find the God equation, tell me first. We'll split the Nobel Prize money together, you and me. Here's a question from Princeton University Press, and that is, who is your favorite physicist? 46.2% said that Einstein was their favorite physicist. 53.8% thought that Richard Feynman was their favorite physicist. My favorite physicist is Isaac Newton. He asked the question for the ages. If an apple falls, does the moon also fall? And he realized that he didn't have the mathematics to calculate a falling moon. So what did he do? He invented his own mathematics called calculus. And the theory was one of the greatest theories of all time, Newton's law of gravity. And so during the Black Plague of 1666, one of the greatest minds in history went from superstition and thrust us into the age of mechanics, the Industrial Revolution. He changed world history. You can't beat that. Einstein is way up there, so is Richard Feynman, but Isaac Newton tops them all. The next question comes from Hassan Babajo, who asks, can light bend around corners? If yes or no, give one reason. Yes, light can bend around corners. In fact, that's why we have glass inside your glasses. When light goes into glass, it slows down slightly. Because it slows down, it deviates from a straight line. And that's why we have your glasses, telescopes, microscopes, because glass bends light. Also, gravity can bend light, as Einstein showed us, and we can actually see the bending of light as it goes around a galaxy. Then the next question is, can you bend light completely around an object so the object becomes invisible? And the answer is yes. It's well within the laws of physics that if you could govern the atomic structure of glass, then light would bend in a way such that it would completely go around an object, so anything inside that object becomes invisible. One day we will build a metamaterial out of nanotechnology that will bend visible light so that anything inside that capsule will become invisible. Harry Potter, watch out. BoxyFan 2001 asks, how do black holes distort time, and what the hell does that mean? Time does not beat uniformly throughout the universe. Clocks on the moon beat a little bit faster than clocks on the planet Earth. On Jupiter, clocks beat slower than on the planet Earth. The heavier the planet, the slower time beats. This means that on a star like the sun, time beats even slower. And the ultimate star, of course, is the black hole, the remnants of a dying star. We think that at the very center of the black hole, time stops. What does that mean if you were to fall into a black hole? From your point of view, it would take perhaps a few minutes, let's say, to fall through a black hole, depending upon where you started from. Your watch says that you went right through to the center of the black hole. But from outside, somebody with a telescope looking at you from outer space would see you frozen in time, slowly going into the black hole, because time beats at a different rate from the outside and the inside. Get your head around this. Time can beat at different rates at different points in the universe. Shelby asks, how are black holes and infinite density even possible? How does something get so dense that it collapses on itself? I want to know. We know that if I take a gigantic star or galaxy and compress it, its gravity is so great that nothing known to science can escape the clutches of gravity. So light itself is trapped by the black hole, and according to textbooks, it collapses to a point of infinite density. Let's be real about this. There's no such thing as infinite density. We just say that in textbooks because we don't know what happens when a star collapses into a tiny dot. Infinite density is a shorthand of saying, I don't know. We really don't know what happens at the very center of a black hole. If you do the mathematics very carefully, you realize that the black hole is spinning, and spinning stars collapse to a ring. They don't collapse to a dot at all. And if you fall through the ring, the mathematics says that you fall not just to the ring, but you fall to the other side to a parallel universe. That is, on the other side of a black hole, there's a white hole. Everything that falls in gets blown out the other end. The Village Celeb at the Village Celeb. Here's a question for physics people only. I was sitting in the backseat of a bus, which was going at 120 kilometers per hour. A fly rose from my shoulder and flew right up front and landed on the driver's. So does it mean the fly was going faster than the bus? Let's let Newton answer this question. And that is, velocities can add. If you are a bystander looking at the bus and the fly from outside, you would say, yes, the velocity of the fly is the velocity of the bus plus the velocity of the fly inside the bus. Velocities can add. Now, of course, if you're inside the bus, the fly seems to go at a very slow rate. If the bus is really a rocket ship traveling near the speed of light, and a fly flies inside the rocket ship, apparently breaking the light barrier, how's that possible? Well, Einstein would say that you cannot add velocities in relativity. The fly cannot break the light barrier. No matter how fast that rocket is moving, no matter how fast that fly is moving, you cannot go faster than the speed of light. Newtonian physics is wrong. That means that the two velocities have to be adjusted because of the fact that time inside the rocket has slowed down. Now, this is amazing, but it works. And this has been measured repeatedly with our particle accelerators and our experiments. David H. App Highwell asked this question. What is dark matter? Can it be touched? Is it dangerous? Most of the universe is made out of dark matter. Dark matter surrounds the Milky Way galaxy. If it wasn't for dark matter, the Milky Way galaxy would have spun out of control and the Earth would be flung into outer space. Can it be touched? Well, no, because it would filter right through your fingertips, right through the atoms of your body. Is it dangerous? No, because it doesn't interact with us. And then here's the big question. What is it? There's a Nobel Prize out there waiting for that person who could figure out what dark matter is. Heeks at Hikitak asks, what is the difference between experimental physics and theoretical physics? Experimental physics engages in reality. It does experiments on things you can touch and feel. Theoretical physics tries to explain how and why that happens. Einstein did not do experiments on light beams. He did not do experiments on stars and galaxies by looking through a telescope. Einstein worked with a pencil and paper. That's called theoretical physics. And the heavy lifting was done by experimentalists who built the particle accelerators, the telescopes, and the devices that allowed us to probe into the center of stars and galaxies. Jihan H. asked the question for physicists: is adding a cape to your superhero costume enhance your flying abilities? I wish that there was a magic cape that we can suddenly put on and soar like Superman. It doesn't work that way. Birds fly not because they flap their wings. Birds fly because of the shape of their wings. The shape of the wings is an airfoil, a tear shape for the bird's wing. Air flows over the tear and under the tear, creating a partial vacuum on top of the wing. That partial vacuum means that air has to flow upwards to keep that wing afloat. It is Bernoulli's principle. So it's not the cape, it's the shape of the wing that is the key to flying. These are the questions for today. And remember, there's no such thing as a dumb question. Years ago, when a young boy was 16 years of age, he asked a dumb question: can you outrace a light beam? That 16-year-old boy was Albert Einstein. And that dumb question opened up the universe for physicists and for you and me. Thanks for watching Physics Support.